Okay, on to the last problem, question 5 here, and I'm sorry I'm zooming out a little bit just because it is a big problem. There's a lot to show, and I want to be able to have both things, or multiple things up on the screen at a time. So hopefully you can still see what I'm doing with the zoomed out version. So question 5 here, a hacker discovers a program that takes command line arguments and is vulnerable to a buffer overflow attack based on a string copy in a user-defined function. He decides to perform some recon of the program using GDB. His first step is to print out the assembly code for the main function. So after setting a breakpoint in the main function and running the program with a particular command line argument, the hacker types IREBP and gets this result. We'll save that for later, but first it asks, what's the value of the return address? So at the bottom here, what's the value of the return address? So how do we find that? At this point, we don't know anything really. We could maybe potentially find it in this mess of hex over here, but that's going to be difficult. It's probably going to take you a lot of time. So what you want to do is, that there's a bug in the user function, right? So we're stopping at that call, and the return address is always going to be find the call and then go to the next instruction, because what we want to do is go into this code, right? We're going to jump somewhere else, and then when we come back from that code, we want to go to the instruction that we haven't executed yet, right? Whenever we come back from user func, we want to go to the next line of code. And so our return address is going to be right here at main plus 32 or OX048408. So that's going to be our value, OX08048408. Okay, I'm going to keep this up for a second here while we look at the other questions. So part B, locate and circle the return address in your hex dump above. And so here, we're looking for that value that we just wrote down, keeping in mind that it's going to be in little endian, right? So if we convert that to little endian and think about what it's going to look like, we're going to take each byte and sort of flip it. So we're going to look for 08840408 in memory. So that's the sort of little endian value that we're trying to find in the haystack over here. Luckily for us, it's sort of right at the bottom of memory here, so we can find that is the return address. So we would circle those 4 bytes. And we can verify based on the information that we're given over here. So we're given that our EBP is BFFF F7F8, right? And the next thing in memory after our return address, based on what we know about the format of the stack, is that it should be prior EBP. And so if that's the EBP that was in main, we should see this BFFF7F8 that we were given as the prior EBP value right after the return address, right? So that's our return adder, and prior EBP is there. We do want to kind of keep track of the addresses here, right? Just noting that this address matches up with the address on the bottom. Since this is a buffer overflow problem, we can kind of expect that like something's getting overwritten as we move on here. Okay. So I'm going to move out this first page. We don't need it anymore. Next, we're looking at, for part C, write down the address where the return address is stored. Well, we know what this is. That's our return address, right? So we just need to know the address of it. And if we look over here, this is the address of that first byte, right? So this is the address of F8. So E8, 7E8 is here, 7E9, 7EA, 7EB, 7EC, right? So we can just count over, and I'm just going to shorthand it, right? It's 7E8, 7E9, 7EA, 7EB, and then 7EC. So that whole first part, BFFF 7EC, is our answer there. Okay. Let's move on to the next page. And we're going to still need our stacks here to be able to answer our questions. So we've got part D. What is the size of the no-op sled in bytes? So this is after, this is sort of the beginning, before, and this is the after the buffer overflow. So this is just giving us some information on where stuff is in memory. This bottom one is telling us, what happened as the buffer overflow executed. So what's a no-op? We need to know that a no-op is OX90 in machine code. So we do need to know that fact to be able to do this problem. you might be able to, figure it out from this and understanding, what the attack looks like. So we see a bunch of OX90s starting right here, right? So that's our first OX90 that we see on the stack, and we're going to go until we don't see any more, and that's the end right there. So all of those bytes are part of the no-op sled, right? And we're just looking for that particular number in memory, that OX90 that's there, knowing that that's what a no-op is. And from there, we're just going to count, right? This is 8 per row, and I've got 1, 2, 3, 4, 5 rows. So I've got 40 bytes of no-ops as part of my attack, right? So that's just counting the number of no-ops. If you really wanted to, you could count each individual one, but you're wasting time because it's 8 per line, right? So then part E, what is the size of the shellcode in bytes? So here we're going to kind of look and see like, okay, what does the rest of this attack look like? We see after the no-op sled, some random machine code stuff happening, probably, just a bunch of different bytes that we don't know what they mean. They kind of look like ASCII, they kind of don't. But we can see that, there's a bunch of stuff being entered here. And then eventually we get to where it starts to look really similar all of a sudden, right? Bunch of different stuff, and then all of a sudden A8, F7, FFBF, A8, F7, FFBF, A8, F7, FFBF. So it's kind of like pattern recognition that we see that these are all starting to be the same, right? And what we know about an attack is that our buffer overflow attack is that we've got this sort of portion of no ops, we've got some set of shell code, and then we've got repeated malicious return addresses. So this here must be our shell code, and this must be our repeated malicious return addresses, right? So that's all of those things at the bottom there. So how big is our shell code? Again, we've sort of matched up what it is, what it looks like. We just need to sort of walk through and count then to see how many bytes of it we have. So we'll just sort of count down. This is 1, 2, 3, 4, 5, 6 rows. 6 rows times 8 bytes equals 48 bytes. So again, not too difficult, just counting how many things we see in that range. Part F. What is the malicious return address the hacker chose? It should be stated as an answer, not as 4 individual bytes. So we're asking you to, untranslate from little endian order. We know that these are all repeated malicious return addresses from, understanding what the format of this is. And so we have to read this, but read it right to left, write it left to right. So we should have OX, BF, FF, F7, A8 as our malicious return address. Again, this is in little endian order. So we just read it across from right to left and then write it left to right. Part G, did the hacker successfully overwrite the return address? Justify your answer. Note that this is not asking whether the attack will successfully execute the shellcode. So we're just asking, did this up here get overwritten down here? And clearly we can see that like that address, yes, address OXBFFF7EC, which we identified as the return address in the previous questions, was overwritten by the malicious return address. Okay, so then will this succeed? Whether or not it will succeed. So we know that it overwrote the malicious return, overwrote the initial return address. So that value is going to get put into EIP, right? So it's going to execute some code from the stack that we put in. The question is it going to execute the right code, right? We know that it needs to sort of, based on our diagram, we've got our no-op sled, we've got our shell code, and we've got our repeated malicious return addresses. And those are going to redirect us somewhere up into the stuff that we've inserted. And we need that to redirect between the no-op sled and the shell code for this to work, right? So regardless of where it actually ends up, it's got to be in that range to be successful. So we want to look at our address that's actually there, and then look at the addresses over here and see, okay, where is BFFF F7A8? And that's right here, right? So we find that address, we look at where that's pointing to, and we can see that that's in the middle of the shell code, right? So it's not in the no-op sled. It's not the first byte of the shellcode. In fact, the last byte that we needed to use, or that we could use, is that 798 right there. That would point to the very first byte of the shellcode. And anything above that in the no-op sled will also work. So no, it will not succeed because the malicious return address points into the middle of the shellcode. All right. So then last one, state one modification the hacker can make to the attack to cause it to succeed, i.e. ensure the shellcode will execute. And I would just say for this one, change the malicious return address to OX BFFF798. And that points to the beginning of the shellcode. So we know it's going to be safe. You could choose any address within the no-op sled as well. You could also say things like, we use a different shellcode that makes it smaller so that malicious return address works now, right? So there are a bunch of different answers to this question. As long as you justify it well, I think you'll get points for it. So that's it. Sorry, that's a long question and a little bit of a long exam. I hope this helps you prepare for the 6th week. Good luck.